even though it's an absurd place to record.
That's fine.
Yeah, and I'll just list it somewhere and send you the link. Anyway, so what we've got here is this Ricci tensor then, which is a contraction of the Riemann curvature tensor. It's the commutator of, you can think of it as a commutator of what in Yang-Mills theory are called covariant derivatives. And since we're working to lowest order, gamma k times gamma L, we just drop that because the gammas are already of first order. So there's one gamma times another gamma second order in H, so we drop it. So the Ricci tensor is just this funny, I guess, antisymmetric combination of derivatives. And then if we remember what gamma was in the weak field approximation, then this expression here is just this. And then two of these terms cancel, and we're left with this. And this first term is the one that we're going to keep because it is, we can write this as RIL is 1/2 box on H L comma I plus dot dot dot. Box wait a minute. I'm afraid I just made a mistake. All right, I made a mistake here. I was not being careful. What we've got here is minus 1/2, and the thing that is the box term is this. So it's box of HIL, and this is a box in the sense of one upper derivative, one lower derivative summed over them. So in other words, it is grad squared minus d0 squared, minus d by dt squared. That's what this is. And and these other terms here, we can remove by a coordinate transformation. And what we do to get rid of the extra terms is we say, so this is the equation I just wrote down. RIL is equal to minus 1/2, and box being another way of writing box, of course, is d upper k, d lower k, which is, again, as I said, grad squared minus d0 squared. And that's the wave equation. Now, the details of this are in this exercise 13.19. And I think this is kind of technical and boring. I tell you what I'll do. I'll send you the solution. I'll send you the details of the exercise as a PDF. In fact, so I don't forget, let me do it right now. So 1007 1008 and I'm going to call this thing 13.19 save. And so as not to forget, I'm going to send you this then. Okay, so that's the details of this. This is a particular trend. This is the choice of coordinates is traditionally called the de Donder gauge. In any event, it's a gauge that gets rid of these three components by making a small gauge transformation. And so it's basically x prime I is equal to xi plus epsilon I j xj plus what was I going to say? How actually, I'm a little confused now. Hold on. Well, yeah, no, let me change that. That I was being sloppy, very sloppy there. It's just epsilon I of x, and so that's this. Of course, is a general. This is a small coordinate transformation. Okay, so anyway, we eventually get what you have then is a wave equation for HIL, which is the departure from the flat space metric of the metric of space-time as the gravitational wave comes through. And it's a wave because it satisfies the wave equation. And as I mentioned, LIGO, back now, it's 7 years ago. So this is really becoming a mature field now. Let me see if I can move this away. One of their early detections was two black holes, one of 29 solar masses, one of 36, and they came together and formed a black hole that was not the sum of their masses, but it was the sum of their masses minus 3 solar masses. And so that much energy was liberated. If gravity were as strong as electromagnetism, it would have just probably extinguished, it would have disrupted probably the whole galaxy in which it occurred. But because gravity is so incredibly weak, in order to detect it here on Earth, one needed the LIGO detector. And in fact, when people were first discussing the detection of gravitational waves, I thought they were out of their minds. I thought it was a boondoggle, and I thought that it was just people who wanted to get extra funding for lasers and quantum optics.
I've got a conceptual question about that.
Yeah.
So is gravitational radiation kind of an analogous to, I guess, normal like photon radiation? Like in the sense
It's
that
analogous.
Increase.
It's completely analogous, except for two things. The photon has spin 1, the graviton has spin 2. And secondly, the photons interact conveniently. That is to say, the interaction is weak enough that we can use perturbation theory to understand electrodynamics, electricity and magnetism, quantum electrodynamics, but it's strong enough so that it makes a difference and atoms can form, life can go on, and so forth. Life being essentially an application of, quantum mechanics, electricity and magnetism, and anyway. Whereas the gravitons interact incredibly weakly, and so in fact, we talk about neutrinos interacting weakly. So a low energy neutrino can go through light years of lead without interacting once. Gravitons interact far more weakly than neutrinos. I mean, it's just absurdly weak. That's why you could have an explosion of this magnitude, I mean, 3 mass of the sun, c squared. I mean, this is just, you know, completely off scale when it comes to energy. But when it hit Earth, it didn't destroy life on planet Earth. It was just barely enough to be detected by the LIGO detector, which is incredibly sensitive. But you may have wanted to ask other things in your question.
Yeah, so then is there an analogy to like entropy? Like is there like gravitational entropy throughout the universe too? And like that's always increasing as mergers happen and as mass sloshes through the universe?
I think that that's the case, yes. And I think we had a colloquium that had something to do with that. I don't quite remember. That's entropy has been a puzzle that people, for example, were saying the following: you have a black hole. You take an encyclopedia, which has all sorts of information in it. You know, we think of the information as what's written, but it's also the arrangement of the atoms and everything else. And all that goes in and to the black hole. And then the black hole, when it eventually evaporates, it evaporates by radiating energy, I guess primarily photons, very slowly at first, and then very quickly when it becomes very small, and eventually everything is radiated as thermal radiation. And so the thought is that we've had, I guess I'd call that an increase of entropy. A lot of information went in, and what came out was just black body radiation, which has more entropy. And
Yeah, that's kind of what I was thinking with these mergers. Like there's concentrated densities of gravity and potential, and then they kind of slosh out and expand throughout the universe, like and
yeah,
occupy more states.
right. Yeah, I frankly have never thought a great deal about that particular point. My understanding is that it was thought to be, like 20 years ago, it was thought to be a real paradox. And just, in other words, in the mid-70s, that English guy who unfortunately died because of that disease he had, Hawking, pointed out that black holes weren't really black because they radiated, and the radiation wasn't very much, but it was enough so that eventually the black hole would go away. And so shortly after that, people thought there was a real puzzle, and then more recently, I think the thought is that that's not not so much of a puzzle. But frankly, I never, to be totally honest with you, I skipped undergraduate thermodynamics. And as a graduate student, when I had thermodynamics or statistical mechanics, the professor was Roy Glauber, who was my thesis advisor at the time. And his lectures were so clear that I thought I didn't need to do any work in the course. And so my actual background in things like entropy, it's weaker than it should be. And that's a little bit bizarre, because one thing that I've worked on was path integrals and path integrals in, well, it's said to be Euclidean space, but what it really is that you're just computing average values of e to the minus h over kt. And so I've sort of worked in the field, but it's not a field that as a student I ever worked on. I essentially, I thought it was trivial, and so I blew it away and didn't pay much attention.
That was the hardest for me in undergrad, I know.
Oh, really? Thermo and StatMech were the hardest things you had as an undergraduate?
I think so. I mean, because they always differentiate between like photon gases, bosonic gases, fermionic, and then like phonons, and then like mixture systems, and like everything has like a partition function, and it's like keeping it all in your head is like, I don't know. It was just really hard.
Yeah, well, the other thing is that all those concepts really make sense in terms of quantum field theory, and undergraduates usually aren't taught quantum field theory in any detail. I guess sometimes in their senior year of college, they may have a chance to take quantum field theory, but most undergraduates in physics today, I don't think get any quantum field theory at all. And these concepts are really concepts of quantum field theory. Well, anyway, let's just go on a little bit. What happens here then is that this is a spin 2 object. And so you'd write this thing as a 5 vector, just as at least the spin part as a 5 vector. And so you could have 5 different components, 2, 1, 0, -1, -2. But because of gauge invariance, or I should say coordinate invariance. Well, let's go back to electrodynamics. In the case of electrodynamics, what you have is you have a condition that we normally apply, a gauge condition, which is Ki epsilon I equals 0. And so that's the Lorentz gauge. And well, that's the Lorentz gauge. A better gauge is that an easier gauge to think about is the Coulomb gauge, which is that the divergence of A vanishes. And so then what you have is K dot E equals 0 and K dot B equals 0 and K dot A. Of course, when I said K, what I really meant, I was really speaking in Fourier space. So it's really just divergences. And what that means then, if you write A as some sum or integral of polarization vectors, so let's times hell, I don't want to do that. Hold on. Well, no, wait a minute. So here I'm doing a sum over K and lambda. And the condition then is, plus the complex conjugate of these things. So this is the way you write the electromagnetic field in the Coulomb gauge. And you have then this condition that K dot epsilon is 0. And so that takes you from having the spin of the photon being, being, say, up, horizontal, and down. All you have is up and down. And so the spin is either parallel to the direction of motion or anti-parallel to the direction of motion, or a linear combination of the two. And similar things happen with the graviton. You have the gauge conditions that I just mentioned here, and those gauge conditions imply that the spin of the graviton is either parallel to the motion, to the direction of the motion of the graviton, or anti-parallel to the direction of motion of the graviton. And so it's 2 units in the direction, in other words, it's 2 units in the direction of motion of the graviton, or 2 units in the opposite direction of the motion of the graviton. And so in that sense, it's very similar to electrodynamics because, or to photon radiation, because both particles move at the speed of light. And there are these gauge conditions that eliminate the possibility of the angular momentum being in any direction but parallel or anti-parallel. But the difference is that the gravitational waves are just so incredibly weak compared to the electromagnetic waves. So let's see. We were going to go to another topic. I mean, we're sort of out of time. We can quit now. If you want, I could chat for a few more minutes. I gather you want to go to dark energy now, or do you want to stay with gravitational waves?
We could move on to dark energy and just like, yeah, you said like no one has any definitive answers, but like I'd love to hear some of like the top theories or any kind of like research papers you find particularly interesting.
Yeah, it's something I've been thinking about for a very long time, or it's related to something that I've been thinking about for a very long time. And the thing that I've been thinking about for a very long time is these infinities in quantum field theory. And the problem basically is that if you imagine you have a bosonic field, then the Hamiltonian is the sum of, so let's say just a scalar field for simplicity. Then you sum over all momenta, and the energy is the energy of that momentum times what we call a dagger of that momentum, a of that momentum plus a half. So that's the Hamiltonian for a free scalar field. And this part is okay. But the implication then is if you take the mean value in the vacuum, or the average value in the vacuum of the Hamiltonian, what you get is 1/2 the sum over k of omega k, and omega k is the square root of k vector squared plus m squared. I'm always using, whenever I'm talking about quantum field theory, I have h bar and c equal to 1. So this is the problem. This is the ground state energy. And if we switch to continuum, the continuum case, and this is d cubed k, square root of k squared plus m squared. And this is then 4 pi, so this is 2 pi integral k squared dk of square root of k squared plus m squared. And we're integrating 0 to infinity. And so this is the lowest order. It's 2 pi times infinity to the 4th power over 4, if I'm right. Let's see, it's k cubed, right. It's absurd. It's pi over 2 times infinity to the 4th power. And so what people say, well, we renormalize the theory in some way. And so we put in, we say that this is really pi over 2 times the Planck mass to the 4th power. And so we get some absurd number. And the fact is, so in other words, this is something like 10 to the, I don't know, let us say 19 to the 4th power. And on the other hand, the actual value of the Hamilton of the dark energy is something like 10 to the minus 3 electron volts to the 4th power. And so the error then is something like 10 to the 19 divided by 10 to the minus 3 to the 4th power. So it's essentially 10 to the 22 times 4, which is 10 to the 88. Some people use a bigger number. I don't know quite why, but anyway, it's that's a, so in other words, what we've got here is, what I find most upsetting is this part, that we've got infinity. And even if we cut it off for no good reason, we get 10 to the 88, and or something too big by that amount. And so, so that's the puzzle. I can tell you about some ways that some people have thought of dealing with it. I can't easily tell you all the ways that people have thought about dealing with it. I can tell you some ways that I've thought about dealing with it, and some ways that other people have thought. And what many people have done is said, well, somebody's going to solve this using a better version of quantum field theory or string theory or something more advanced than string theory. And what they'll eventually get is 0. And what makes sense then is to imagine, is to compute physically and simply in a theory with no infinities what the small energy density is, and have a model for that and think about how that affects cosmology and so forth. And so I can tell you something about some of those theories. I mean, when you know, in the future, when this thing is worked out theoretically, there'll either be a theoretical explanation of why it's small, or the theoretical explanation will be that the thing is 0, and except for this effect, which has nothing to do with with the average value of the energy in the vacuum, that being exactly 0 in a physics that will be understood in 50 years. So that's basically the situation. So we could talk a little more about that. And so have you had a course yet in quantum field theory?
No.
All right,
no,
so
I haven't.
why don't we do a little quantum field theory so that you understand here, understand this stuff, and then and understand, you know, what the problem is, and then some ways that people have thought of solving it using supersymmetry, some ways I've thought of solving it, and then we can go on to the people who are more practical and say, well, we'll let somebody else solve that. Let's just think about the physics of finite average vacuum energy. All right, so we're over time, so we ought to quit. Let me see if I can. So if you have one last question, I'll try to answer it. Otherwise, we'll just stop.
No, I'm good.
Okay. All right. Have a nice week. Take it easy.
Have a good weekend.
Bye.
Bye.